In this short video, I'm doing a power example where we're looking at finding the power associated with each element. So that's the problem statement. Find the power associated with each element. So it's going to be important to find both the total power in watts, but also whether the element is using or supplying power. Okay, so let's start with element A. All right, so with element A, we can look, here's the current 4 amps coming right through here. And so we know the voltage across A, and we know the current through A, so we can get the power associated with A. Okay, so it's going to be 15 times 4. So that'll be 60 watts. Now, the sign convention is the current is moving in the direction of a voltage drop, so it's the passive sign convention. Therefore, this is using. Okay, moving on to element B. All right, with element B, we don't know the voltage across it, and we don't know the current through it. So we're going to have to find that. All right, so if I look here, I see that B and D are actually in parallel. So if I write a little loop equation going this way, I have a rise of 20 and a drop of plus minus VB. Okay, so the rise is equal to drops. So here's a 20 volt rise, and that's equal to a drop of VB. So VB is equal to 20. Okay, then we also know that 4 amps is here and 2 amps is here, so that means this splits, and a KCL equation at this node would give me 2 amps coming down. So I know now the current through VB. So the power associated with element B is 20 times 2, which is the 40 watts. And again, this goes from plus to minus, so it's the passive sign convention. So this is using. Okay, element C. Okay, element C, I have 4 amps coming down this way. It's still, this is the same branch, so this is 4 amps. Okay, I also need to know the voltage across, so I need to know VC. Okay, so I have to write a loop equation. So I could write a loop equation and I could go in this direction. All right, so I see I have a drop of VC. The drops are on this side, the rise is on the other side. And then I have also a drop of 15. Okay, then moving along this way, I have VB, a drop of VB, so VB is 20. And now I'm done with the loop. Okay, so that's equal to 0. So I can get VC, and it would be minus 35 volts. All right, that's not a problem that it's minus. Okay. All right, so now let's calculate the power associated with C. That's going to be minus 35 times 4. So that's 140 watts, minus 140 watts. And the sign convention I'm using, here's the current. It's going in the direction of a drop. Okay, it goes from plus to minus. And so that's the passive sign convention. So it's using minus 140 watts, which is the same thing as 140 watts supplying. So you see the signs take care of themselves. All right. And then onward to element D. With element D, I have 2 amps. It's a passive sign convention, 20 volts. Okay, so PD is 2 times 20, which is 40 watts. And since it's passive, it's using. All right, so if I looked at elements A, B, C, and D, and I classified that as either using or supplying, then what I know is that element A is using 60 watts, element B is using 40 watts, element C is supplying 140 watts, and element D is using 40 watts. So when I total all these up, I get 140 on the supply side and 140 on the using side, and we have a power balance. Okay, so I like that kind of problem. Hopefully it makes sense to you. And there we go.